All right, second lesson is on the fundamental theorem of calculus. Fundamental theorem of calculus ends up talking about how we can find areas under curves using a calculus idea of an antiderivative. We thought antiderivatives were just like one way to kind of go backwards from like an f prime to an f. But now we discover a great application of antiderivatives is to find areas under curve. Discuss two ways one can find distance given a velocity function that is positive and a position function that you can find. So here's an example. So I just want you to kind of think about the pictures where you could think about distance being velocity times time. Okay? So let's say we have t squared. Here's v equals t squared. If I take a bunch of velocities times times, I will be looking at like multiplying all of these velocities by the instant that they are at that velocity. So like very large calculations of velocity times these very, very small time increments. So distance could be considered the area under a velocity curve. What we then talked about is how we can represent this area using this integral, and it goes along with the next part of what we're going to do. So I'll just do integral from 1 to 3 of t squared dt. Okay, that's really velocities times the instantaneous time at which they're at the velocity. Or you can think about distance, and it's really displacement could be just equal to our change in our position. Where I can take a final position, or my position at time 3, and subtract our position at time 1. Now what we find is that if we take the antiderivative of v to get x would be 1/3 t cubed plus c. And it's like, oh, they didn't give me enough information to find c. But if we do some calculations, and knowing that c is going to be just a consistent number, if I plugged in 3, I keep the c, and then if I plugged in 1, I find that the c's will go away. This c will cancel with this c, and I end up with an answer which is 3, 9, 27, 9 minus 1/3. 27 thirds minus 1/3, which is 26 thirds. There's your answer. That is how we find area under a curve. Instead of trying to do velocities times times, we don't have enough time to kind of do an appropriate calculation to get that. If I want to find the area under a function, which I'll just say 1 to 3 of, x squared dx, if this is f of x equals x squared from 1 to 3. All we need to do is just take the antiderivative, understand that the c is not needed because we will find the change in the antiderivative. I like to put this line here to represent we're finding the change. And again, we'll do the work to get 9 minus 1/3, which is 26 thirds. Okay? So this is a key concept in calculus, area under curves. And this was a big problem in math circles. They didn't know an effective way to solve it for all situations. Calculus and antiderivatives in particular helped solve it. Okay, so it's like kind of like the second major thing in calculus. The first major thing was was finding slopes of tangent lines, and then the second major thing is finding areas under curves. Okay. Now, what's great is that if you have straight lines, here are some straight lines, you could find the area both geometrically and using the fundamental theorem of calculus. And this is just one way to kind of prove, and not prove, but show you that this antiderivative technique, this finding the position, will work. So here I got y equals 3. So geometrically, I can find this area. It's easy. 4 times 3, that's 12. Okay? But now, using the fundamental theorem of calculus, instead of doing velocity times time, so this is essentially like velocity times time, using the fundamental theorem of calculus, I'll say, okay, well, let's say I didn't know how to do velocity times time. I have the equation y equals 3. I'm talking about finding the area between 0 and 4. I will take the antiderivative of 3. I get 3x. I find the change between 0 and 4, and I'm sorry, it's 3x plus c. That's the antiderivative, but the c will go away when I plug in 0 and 4. I get 12 minus 0. That's 12. So I get the same answers, really, 2 different ways. Maybe that's not easy to see the differences with this one, but let's do this guy, which is a triangle worth of area. So using geometry, the area would be 1/2 my base times the height. And again, this is kind of the velocity times time way to calculate distance. I need to find this value. If I plug in 6 into x, I get 3. So my area is 1/2 my base length, which is 6, times my height, which is 3, and I get 9. Okay, so that's one way to find this area is 9. But now, using the fundamental theorem of calculus, I say, you know what, maybe I don't know how to do velocities times times. So I instead say, okay, let's take this alternate approach to find area, and this is like kind of our expression for area. We can take the antiderivative. The antiderivative of 1/2 x would be x squared times 1/4. So the 1/2 times 1/2, 1/4. Remember our antiderivative rules. Plus a c. But when I find my final position minus my initial position, so I find the change in my antiderivative, I don't need the c. I just have 1/4 6 squared minus, find the change, so we're subtracting, minus 1/4 0 squared. I get 36 divided by 4 minus 0, which is 9. Okay? We get the same answer 2 different ways, and we can see the calculations are definitely different. 6 squared divided by 4 is not 1/2 times 6 times 3. Okay, so very different way to calculate the same area. Okay, and remember, it's the change in position, a final position minus an initial position. And it's really not a final position minus initial position. It's more just like you're calculating the displacement because you don't know what c is, but c won't matter. Okay? Now, here's another one. What we talked about, and we talked about briefly, and you had to add this into your notes, is that when you're doing areas, and this will make more sense next class when we talk about distance versus displacement. Let's see, I got to do some work here. I got 0, this will be a -6 here. I got 5, which is, this is 4. You think you got kind of 2 areas. You got a 1/2, a base length of 3 and a height of 6. And then you add 1/2, a base length of 2 and a height of 4. And you think that the area because you know area is positive, is, let's see, 18 divided by 2 is 9, and plus 4, 13. But watch how if you want the other way, it's going to get you a different number. And then that goes into why we're going to say that this area is negative. I'll take the integral, I'll find the area from 0 to 5 under 2x minus 6. Okay, so I start by taking the antiderivative. I got x squared minus 6x plus c. I won't need the c because when I find the change, the c's will go away. I end up with 5 squared minus 6 times 5. And then minus, I'll have 0 squared minus 0. Okay, so that's 25 minus 30. I get an area of negative 5? What? Turns out this is what we're going to say is correct. And there's a reason why. We will say that this height of negative 6 is negative. And this should be a negative 9, which means this turns into negative 5. And that's because if you think about this in terms of like a velocity, and we'll talk about this more in next class. If this was a velocity, well, this negative velocity would mean I'm traveling to the left. Well, the negative velocity traveling to the left would mean my displacement would be negative, or the change in my position would be negative. And then my velocity here, positive, means I'd be going to the right, my displacement's positive. We could see that I'm going to the left more than I'm going to the right. So what we end up finding, this number here, ends up not being distance, it is displacement if we consider the area below the x-axis negative. We'll talk about how the answer 13 is correct. The answer 13 would be considered the distance that we traveled if this was velocity. But for right now, what I just want you to know is that if you have area below the x-axis, you're going to consider it negative, and the fundamental theorem of calculus will take that into consideration, and you don't have to kind of worry about doing anything fancy. Just do the antiderivative, find the change, you automatically find the correct answer. Here, geometrically, we just have to understand that this height would be negative, and that area is negative. Now, these three, you could have done both ways. Once you have a curve, you no longer can do things geometrically. There's no formula for the area under this x cubed curve from 0 to 2. So if you're asked to do it geometrically, answer is nope, can't. The best you can do, and we'll talk about this in a later unit, is approximate by using like rectangles or a triangle or something. Instead, we can only use the fundamental theorem of calculus. We can only find the change in my position if you consider this velocity to find what ends up being displacement. So integral from 0 to 2 of x cubed, we get 1/4 x to the 4th plus c. That's the antiderivative. The c won't matter when I find the change. 2 to the 4th, 2, 4, 8, 16. I get 16 over 4 minus 0. I get that this area is just 4. Fascinating that the area under x cubed between 0 and 2 is just 4. Yep. E to the 3x between 1 and 3. Can't do it geometrically. We can only do this change in position technique, this kind of displacement calculation using the antiderivative technique. So I'm going to write the integral just so I understand, like I'm going to be taking the antiderivative. We talked about using the integral because we know that the process will involve taking an antiderivative. The numbers are just kind of understanding boundaries. We'll talk about in the future how there's another way to look at this integral as not being just an antiderivative, but for right now, that's all we need to care about. We need to be able to take the antiderivative correctly. Antiderivative e to the 3x is e to the 3x. Don't forget the reciprocal of the coefficient of x. We got a plus c, but we won't need the plus c because we're finding the change. So the plus c's will cancel. I got 1/3 e to the 9th minus 1/3 e cubed. And I would just have to leave it like that. What's important, if I was going from 0 to 3, so let's say I started here at 0. A lot of times when we plug in like 0, when we find the change, things just go away and we don't have to worry about like the final position. But with e to a power, sorry, this is 0, I'd have 1/3 e to the 9th minus, you'd have 1/3 e to the 0. Now that's not 0. So make sure like we're careful while we're plugging in 0. Don't assume it's 0. This would be 1/3 e to the 9th minus 1/3. Okay. Cos x plus 2x from 0 to pi. Okay. Seems like it's a crazy area. Can't do velocity times times. Can't do geometrically. Instead, we'll find the change in the position. We got 0 to pi of cos x plus 2x. Instead of velocity times times, we will do change in position, which ends up being displacement. Could be distance if the velocities are all positive. We'll talk about that more next class. Here's the antiderivative with the plus c. When I do the change, the c will go away. I'll get sine pi plus pi squared minus sine of 0 plus 0 squared. This ends up being pi squared. Okay, pretty cool that this area is pi squared. Okay, just a couple more, same deal, just kind of practice. We got 0 to 2, negative 3x squared plus 6x. Only way to find the velocity times times here, you might think this is a semicircle, but it's not, is to find the change in the antiderivative. We got x cubed times 1/3, the 1/3 and the negative 3 will cancel. I'll just have the negative of x squared. 6 divided by 2 ends up being 3, so this is the antiderivative. You got a plus c, it won't matter because you're going to be subtracting those c's when you find the change in the antiderivative. I'll get negative 8 plus 12 minus 0 plus 0. So that's going to be just 4. The area here under this curve is just 4. Now watch, if you do the fundamental theorem of calculus, this region is below the x-axis, we're going to find that the area is going to be negative. I don't like to say the area is negative. I'd like to say like just, you can think about like the displacement ends up being negative, which means I'm moving to the left. I always like to think about this stuff in terms of velocity and position, which is why I put this into this unit. So here we go. I got an integral from 0 to 2 of what ends up being like the same function that we did above. So we'll have the same antiderivative with just one sign difference. Should be putting parentheses around this for proper. And you guys probably don't realize why we have this dx, but just like when you take the antiderivative, you need to take the antiderivative with respect to x. That's one way to think about why we need the dx. I need it over here to be proper. Okay, anyways, we got, just like the previous one, antiderivative x cubed minus 3x squared plus c. We won't need the c because when we subtract the final position from the initial position, the c's will cancel. I get 8 minus 12 minus 0 minus 0. I might as well like throw the plus c's in here, just to show you, like, even though I don't want students to forget about the plus c's. Like, if I had a plus c here, I'd be subtracting the initial position, which is 0 minus 0 plus c. The starting, this ends up being our starting position. It doesn't matter. And this is not really the initial position. It's kind of, it is the initial position if we know what c is. C minus c is gone. 8 minus 12, negative 4. Notice the areas are opposites of each other, though it's the same function kind of over the same interval. Okay, so we got what we're looking for. We're good with that. Sometimes they won't even give you the picture. They'll just ask you to evaluate this. You can think about this as being like, okay, find the area under 3x squared minus 2x from 0 to 2. It's just already set up for you to go ahead and take the antiderivative and evaluate it. Evaluate the change of this between 0 and 2. So this is 8 minus 4 minus 0. Some other ones, just kind of some practice of antiderivatives. Remember, the antiderivative of 1 over x squared is not log absolute x squared. Wrong. I'll put that up here. Instead, you'd have to rewrite this as x to the negative second. And remember, you add 1, so that's x to the negative first times negative 1. I'm going to rewrite that as negative 1 over x. Find the change in that between 1 and 4. So I'll have negative 1/4 minus negative 1 over 1. That's negative 1/4 plus 1, which is 3/4. It's cool. 1 over x squared looks like this. It's kind of like 1 over x, only it's this and this. But between 1 and 4, this area is just 3/4. A couple more practice of antiderivatives. This antiderivative is 1/3 x cubed minus 4x plus c. But when you find the change, the c's won't matter. You get 8/3 minus 8 minus 0. That's 24/3. 8/3 minus 24/3 is negative 16/3. So x squared minus 4 ends up, the area from 0 to 2 is negative. So here's that negative answer. That's okay. Just understand, if you're below the x-axis, your area is negative. Remember that the antiderivative of 1 over x, the power rule, does not work. Its antiderivative is log absolute x. Don't forget the plus c, but it won't matter. You get log 4 minus log 1. Log 1 is just 0, so I just get log 4. A couple more. This is sine of 2x. It's cosine of x. The antiderivative of sine is negative cosine. But I'm not going to forget the 1/2, which is the reciprocal of the coefficient of x when I'm taking an antiderivative. Cos x is antiderivative of sine x. From 0 to pi over 2, let's do a little bit of work here. I'll have negative 1/2 cosine of pi plus sine pi over 2 plus c minus, I guess I don't need it, but whatever, I'll put it there, minus negative 1/2 cosine 0 plus sine 0 plus c. Okay, it's very important when we're subtracting the entire thing. So distribute this or find this whole thing. I like to just distribute right off the bat sometimes. That negative c, that plus c is gone. That's why I didn't need this plus c. Cosine pi is negative 1, so this is a positive 1/2. This is the sine of pi over 2, which is 1. This turns into another positive 1/2. This is 0. So I end up with 2 as my answer. Seems like it's super complex. If you look at the graph of sine 2x plus cos x, you would think the area is a lot more complicated, but it's not. Let me just make sure everything's correct. If I plug in pi over 2, I get pi. Cosine pi is negative 1. I have that becomes positive 1/2. Sine of pi over 2 is 1. Subtract the negative, turns into add a positive, and then, yep, you're good. Fractional exponents, remember, just use the power rule. Add 1 3/3 to 2/3 becomes 5/3. Don't forget the reciprocal of the new power. Okay. Now we have to do some calculations. 3/5, 8 to the 5/3 plus 16. C won't matter. When I subtract 0 plugged in, I just get 0, which is nice. Okay, cube root of 8 to the 5th. So that's 2 to the 5th, 2, 4, 8, 16, 32. So I have 3 over 5 times 32 plus 16. I'm going to have to stay with the fifths, unfortunately. 32 times 3 is 96. So I have 96 fifths plus 16. 16 in terms of fifths is 80 fifths. And that's 176 fifths. All right. Cool. We'll talk about next class how your calculator can actually do these calculations. It actually goes about it the alternate way, the non-human approach. And I'm going to do that just to check this answer. It will take a bunch of velocities and multiply by a bunch of like very, very small times. So if you want, and I'll show you this next class, you can do math FNINT. This ends up being an integral. If you have a different calculator, a newer calculator, if you do math 9, you see the integral shows up. You can literally type in 0 to 8 of x to the 2/3. It shows up nicely here. Plus 2. It will give you a decimal approximation. Understand it's an approximation because it's doing velocities times times. But if I do 176 fifths, I'm going to get 35.2. Okay, so just something we'll talk about, and we'll be using our calculators starting next class, really. Okay. All right, now there are these problems where you're not given the function, but you just kind of understand the concepts that we have been talking about, where you are finding the change in the antiderivative. So like the antiderivative of f prime, I know is f. Okay, cool. It's f plus c, sure. C won't matter. When I plug in 3 and 1, I'll get f of 3 minus f of 1. I can do that easily. Here is big F, f, and f prime. F of 3 is 2. F of 1 is 5. So my answer here is -3. It's not supposed to be a tricky or hard problem. You just have to understand that you need to kind of, take the antiderivative. Don't forget to take the antiderivative. That's why we have that integral there. There's another reason why we have that integral there. But for right now, the integral means take the antiderivative. So don't forget. And the numbers are just to make sure you understand the change. So if I have f double prime, its antiderivative is f prime. Plus c, sure, but we don't need the c. I need f prime of 5 minus f prime of 3. F prime of 5 is 8. F prime of 3 is -3. 8 minus -3 is 11. Okay, notice the numbers. This is very, very important. This is put in this order for a reason. We'll need to understand ordering matters in the future. This is still my final position. This is still what I can consider my initial. When I take the antiderivative of f to get big F, I need the 2 to go on top and the 4 to go on the bottom. That means I'm not taking f of 4 because it's the bigger number. It's actually saying, you know, f of 2 is my final position. F of 4 is my initial position. So make sure this is our final minus our initial. Big F of 2 is 5. Big F of 4 is 2. So this ends up being a positive number. It's like you're going back in time to figure out a certain position or something. Same thing here. Antiderivative of f prime, don't forget to take the antiderivative, means f. Find the change in f between 5 and 2. This is my final, this is my initial. I need to do, the c's won't matter, f of 2 first, and then I'm going to subtract f of 5. F of 2 is 6. F of 5 is 1. So we're going to answer 5. Remember, take the antiderivative. You take the antiderivative of 3f prime. Remember, constant, just leave it alone. Becomes 3f. You take the antiderivative of 2. It's 2x. Plus the c, there's my antiderivative. I'm going to evaluate that between 1 and 3. So I'm not like adding 2 to like 3f of 3 minus 3f of 1. I'm going to add 2x. So now my calculations are 3f of 3 plus 6 minus 3f of 1 plus 2. Maybe do these calculations separately. F of 3 is 2. So I got 3 times 2 plus 6. And then f of 1 is 5. So 3 times 5 plus 2. This is 12 minus, I'm just going to do the calculations here, 15, 16, 17. So this ends up being negative 5. An antiderivative of f double prime of 2x. You might think it's f prime of 2x, but just like we've done before, you need a 1/2. It's tricky. That's why it's here. Between 3 and 5, get rid of that c. I'd end up, if I plugged in 5 for x, it's not 1/2 f prime of 5, it's 1/2 f prime of 2 times 5. I'll just make sure I write that. And then minus 1/2 f prime of 2 times 3. I screwed up because I bet you I don't have 10 up here. All right, whatever. Just leave it because this is correct. 1/2 f prime of 10, whatever this is, minus 1/2 f prime of 6, whatever this is. I just wanted to show you this example so that you remember how to take the antiderivative. What I could do is change these boundaries to like 1 and 2, and then we'd be fine. Why don't I do that? Alternate integral from 1 to 2 of f double prime of 2x would be 1/2 f prime of 4 minus 1/2 f prime of 2. And then I could find an answer if I change these boundaries. F prime of 4 is 4. F prime of 2 is negative 2. So that's 2 plus 1, which is 3. Okay, this one, just be careful. Take the antiderivative of 2x, it's x squared. Take the antiderivative of 3f, it would be 3 big F. Plus c won't matter from 4 to 2. That means I need to evaluate my final position first, plugging in the 2. I got 2 squared minus 3 big F of 2. And then I'm subtracting 4 squared minus 3 big F of 4. 4 minus 3 times big F of 2. Big F of 2 is 5. Minus 16 minus 3 big F of 4. Big F of 4 is 2. Let's see, I got 4 minus 15 minus 10. So negative 25 plus 4, negative 21. Find the value k to solve the equation. Okay, this is great. From 2 to what value will the area under x squared equal 9? Well, like, this is showing you, take the antiderivative. So I take the antiderivative, I got 1/3 x cubed plus c. Tells me to evaluate this from 2 to k, and that should be equal to 9. Okay, this plus c won't matter. So I plug in k. I took the antiderivative. I now have 1/3 k cubed minus 1/3 2 cubed, and that should equal 9. Well, I can solve this. I don't need a calculator for it. I have 1/3 k cubed minus 8/3 equals 9. I'll add 8/3 to both sides. 9 is 27/3. 27/3 plus 8/3 is 25/3. So I get 1/3 k cubed equals 25/3. Can multiply both sides by 3. I get k cubed equals 25. I then take the cubed root. There's no cubed root of 25, but I get the cubed root of 25 as my answer. Watch how, and we'll talk about this more, how we can use our calculator, and we will be using our calculator more. Integral from 2 to the cubed root of 25 of x squared. Oops. Is what? What did I do? I made a mistake. Oh, 35/3. Haha. 27/3 plus 8/3. 35/3. Multiplied by 3. 35. Glad I caught that. Run it back. 9. All right. What is this 0? Watch this. This is a good one. Antiderivative. Take the antiderivative. X squared plus x plus c from 1 to k equals 0. I won't need the c. I'll get k squared plus k minus 1 plus 1 equals 0. So that's k squared plus k minus 2 equals 0. Are there two numbers that multiply to get negative 2 and add to get 1? Yep. K plus 2, k minus 1. There are two answers to this. K could be equal to negative 2 or 1. Talk about, and it should make sense, if I have an area from 1 to 1, if I'm talking about maybe graphically, the area under x squared from 1 to 1, there's no area there if I'm going from 1 and stopping at 1. So obviously that makes sense that it'll be 0, but also see that I need to go to 1 to negative 2 to end up having, in this situation, 2x plus 1. Looks like that. If I'm starting at 1, I can't go to the right of 1 to get a 0 area. I'm going to have some positive area and some negative area. It's not a good graph. This would be like that. Some positive area and then some negative area. That would have to go to -2. All right, I hope we understand this. This is a different approach from the past and how I introduced the fundamental theorem of calculus. Integrals, meaning antiderivative, instead of velocity times times to calculate distance, and really not distance, it's displacement. Instead of velocity times time, which ends up being visually seen to us by looking at area, we will do change in position. We find change in position by finding the position function by taking the antiderivative. We use integrals to say, hey, take the antiderivative. Take the antiderivative. Find the final position minus the initial position. You end up finding the displacement, or like the distance if your velocity is positive. So this is how we're introducing things. And this is this hopefully makes sense to you. Thank you.